Okay, good morning, everybody. Let's get started. So in the previous class, we looked at the design of different filters, high pass, band stop, and we said there are two methods of designing these filters. We either can design the filter, the intended filter in the continuous time domain, and then we use a bilinear transformation to transform it to the digital domain. And we've done an example with a band stop filter, and we did with a high pass filter. So with these, you're covering, we can do any of the other filters. Now also we said the other method of designing the filters is to design a digital filter and then convert that digital filter from a low-pass filter to any other filter using the table that has the formulas for that transformation. So this is the example that is in the book. So I'm just going to quickly go over it. So this is what the table looks like of the transformation from a low-pass filter to any other filter. So the idea is you design the low-pass filter, then you use these formulas to convert the filter to any other filter. Make sense? So as an example, here is a low-pass filter that has a certain cutoff frequency. So imagine we designed this filter using this cutoff frequency, and then we want to convert it into a band pass filter that has these upper and lower frequencies. And therefore, this is the filter that is the low-pass filter. This is the low-pass filter that is designed with the cutoff of 0.2 pi. And then we're going to...
notification, sorry.
It's me probably saying hi to him at the beginning. It's okay. So we want to take this low-pass filter, convert it to a band-pass filter. So we have to calculate some parameters, A1, A2, alpha, and a K. So just plug in the values of the frequencies in these formulas. We can calculate the K, A1, A2, and then we can calculate the alpha. And when we calculate the conversion that we have to do, it so happens when we calculate it, using this formula, all the A's happens to be 0. So this 0, 0, this is 0, 0. So we're just going to end up with replacing z to negative 1 with z to negative 2. Does that make sense? For this particular example. So therefore, if you replace h of z to negative 1 with h of z to negative 2, it says you're going to be getting a band-pass filter, and this is indeed what we get. This is the frequency response of h of z when z is replaced with z to negative 2. 0.4 to 0.6, which is the pass band of the filter. Does that make sense, everybody? So again, the problem with this method is not intuitive. I mean, there is no explanations as to how the filter is going to behave in the transformation. But nevertheless, here you have seen it and the table of the transformation. Okay. So with that, we are ready to move on to the next topic. And just like on the course map of what we're going to be doing, we're going to finish the FIR filter, then we're going to talk about the filter realization, and then we're going to look at the frequency analysis. Sounds good?
Yeah.
Okay. So our next topic is the FIR filter design. So if you look at the IIR filter, what is it we've done with the IR filter? We said we're going to design a filter, and our filter looks something like this. This is omega, this is whatever cutoff frequency. And then we said, okay, if we look at this filter in the time domain, this filter is going to have some impulse response that's going to generate it. However, this impulse response is going to go from negative infinity to infinity. So this is continuous. This is h of n. And therefore, we are not able to build an ideal filter like this. So this is an ideal filter with a cutoff of omega cutoff. And when we looked at what the impulse response that will generate this frequency response, we said it's not going to be possible to realize or to implement a filter like this because it goes from negative infinity to infinity, and it is not causal. So what is it we've done? We said, okay, let's look at a frequency response that is not ideal. And therefore, what we've done, we replaced the ideal frequency response with a non-ideal response. How did the non-ideal response look like? Depending on the filter, instead of it being, the sharp drop like this, if it was a better one, it's smoothly going down. If it is Chebyshev, we have, the oscillation in the pass band or the stop band. It's not an ideal filter, but that enabled us to create a filter. And this filter that we designed, the IIR filters, are recursive, they are causal, and we want them also to be stable. And we found a free transfer function for these filters, and they were of the form BIZ to negative I divided by the summation of AI z to negative I. And from this h of z, we are able to get the difference equation. We can write y of n equal to A0 B0 multiplied by x of n, etc., etc. That's what we've done with our IIR filter design. Okay. Now, what are the advantages and disadvantages of the IR filters? So we're going to add a plus and a minus. What was one of the advantages of the IR filter design that we looked at, or of the IR filter? One of the advantages was we were able to utilize the analog filter design methods. And that's why we designed the Butterworth Chebyshev. These are well used in the analog domain. And we were able to start with all that knowledge and just transform it to a discrete time domain. Another advantage of the IR filter is that it has a very good performance. And what that means is with a low order filter, we are able to meet the requirements that we need. And a low order filter means low complexity, as we will see later when we look at the realization, lower complexity and lower memory usage in order to implement the filter. what was the challenges or the disadvantages of an IR filter?
You have to have the whole signal.
What is it?
You have to have the whole signal. Like, you can't use it for like real time.
No, not necessarily. You can do it for a real time.
I think you have to know the output.
I mean, depending on the filter order, you might have to need certain number of inputs to generate the output, but that's expected. Any system is going to take some time to process and, to be able to generate the output. The problems with the challenges with the IR filter, the first challenge is that the phase is not linear. Now, we never talked about the phase throughout the class, and all of a sudden now we're saying, oh, the phase is not linear. It came out of nowhere. We'll see why that is important, but there is no point where we talk, oh, now the phase is linear, or we got a linear phase. And that is because in general, for the IR filter, and remember you mentioned something about plotting the phase when we plotted the phase, because that the plot was generated by the FIG of MATLAB, which automatically generates the magnitude and the phase. But if you've seen the phase was not linear. And we'll see why the phase not linear is a problem in a minute. Another challenge with the IR filter is the frequency warping with the bilinear transformation. And another challenge is the frequency aliasing and that comes with the impulse invariance method. And finally, with the IR filter, we have to always make sure that the filter is stable. Together? Now somebody might be also confused, but we talked about the stability. The filter has to be stable, and we talked about all the transformation. It has to keep the system stable. Now we're going to see this in contrast with FIR filter, where we don't have to worry about stability. Does that make sense? So some of these become also even more relevant when we start talking about the FIR filter. So when you go back and look, it will make also more sense as to why we mentioned them at this point. Okay, so with that, we are ready to introduce our next filter, which is the FIR filter. And our objective here is to design a filter such that the output is a function of past, present, and future inputs. How is that different than the IR filter?
It's not possible. We can only do past and present.
What else?
The IIR is a function of future outputs.
It can be a function of outputs too.
Yeah.
The IR filter can be a function of the output. The FIR filter is only a function of the input. Make sense? Now, both of these, present, past, and future, can apply to input and output. But for the FIR filter, we are only, the output is only dependent on the input. There is no dependency on the output. There is no recursion. There is no feedback. I don't have to know the output and store the output to calculate the future outputs. So therefore, if I look at the output of the filter, it's going to look something like this. Summation from negative N1 to NQ, H of I x of n minus I. What does this formula represent? The convolution. The output of the filter is going to equal the impulse response convolved with x of n. Okay, so therefore, we can write this as h of negative n multiplied by x of n plus n1 plus h of negative n1 plus 1 multiplied by x of n plus n1 minus 1 plus h of n2 multiplied by x of n minus n2. Again, this is the convolution of h of n, the impulse response of the filter, and the input. And this is just expanding this summation.
For that first n and the h of negative, is that n1 term?
Yeah, n1. Okay, so therefore, if I look at the transfer function h of z of the FIR filter is going to equal to y of z over x of z, and is just going to equal to p of z. And therefore, y of z is just equal to d of z multiplied by x of z. Unlike the IIR filter, where y of z over x of z was b of z divided by a of z. This is for IIR filter. In the case of the FIR filter, there is no a of z. And you can see it from here too. There is no y, it's only a function of x of n. Y is only a function of y of z is only a function of x of z. Okay. Is that clear? Makes sense? Okay, so what we're going to do is we're going to look at some simple FIR filters that we're going to design by inspection, and then we're going to look at designing the filters using windowing method. So let's start with building some simple filters similar to what we've done with the pole zero placement method. Okay, so the first filter that we're going to look at is the all zero comb filter. What does that filter look like? Anybody remembers that from the IR filter?
The zeros all around and the poles close to
Yes.
it.
It looks like a comb, the frequency response, yes, and the poles are around the unit circle. So we can do something similar. So we can come to our unit circle, and we can place zeros around the unit circle. What is this going to do? What is this filter going to do? It's going to remove all frequencies that have a zero at the unit circle. Does that make sense? This frequency here is going to be removed. This frequency of the input signal is going to be removed. Make sense? Now, in the case of the IR filter, How was the IR filter different than this?
There was poles in your.
There were poles, yes. We placed a pole here, a pole here, a pole at all these locations close to the zeros. In the FIR filter, I cannot do that. Why? Because H of Z does not have poles. Okay, so therefore, if I look at this filter is given by the following equation. Y of n equal x of n minus x of n minus capital N. And therefore, what is h of n going to equal to? Delta of n minus delta of n minus capital N. Okay, what is h of z? 1 minus z to negative n. And therefore, I can write h of z as z to the n minus 1 divided by z to the n. Any objection? I mean, somebody is going to object. Say, oh, you said there is no denominator. Are we inconsistent here? What is this? You just said a minute ago, there is no A of Z. And all of a sudden we have an A of Z.
It'll cancel it with Z.
What is it?
It can cancel back out.
Yeah, I mean, this Z, where is this Z location? Where is this pole location? At the origin. What is a pole at the origin represent? A delay. Does that make sense? So here we have a pole at the origin that's coming from Z to N. But this does not, this represents just a shift in the output. Does that make sense, everybody? Okay. So therefore, we can calculate H of E to J omega. And H of A to J omega is going to equal 1 minus E to J omega multiplied by N. And therefore, I can plot the frequency response of this filter. And this is going to look something like this, depending on the value of N. Is that clear, everybody? So just keep that in mind, please, that anytime you see a pole at the origin, it just means a delay. Because when we multiply it, we're just multiplying, it's going to give you only one term at the output, y of n. Okay, so we can do a Freg Z. So this is what the frequency response of the filter would look like. Together? And again, depending on the value of n that you use, I just put random number of zeros. And if you see the phase, do you notice something about the phase?
That's not linear.
It is. It is linear, but it's warping it.
Yeah.
Like I could unwarp it. It will stretch. Okay.
In small sections.
What is it?
It's linear in small sections.
No, it is linear, but this is when it goes to negative 90, it becomes like 270 and so on. It wraps around. We'll look at it. We'll look at it. Okay. Okay. So if you look at this filter and compare it to the filter of the comb filter that we had with the IR filter, which one is better? IR filter is better. Why? Because give me much sharper spikes here that remove the frequency. Here, if I'm removing the frequency, I'm attenuating all the frequencies next to it. Adding the pole very close to the zeros enable me to make that each of the teeth of the comb much sharper. Make sense? Everybody? Okay. But nevertheless, and what we see here, the output is only a function of the input. There is no dependence on our previous output. And the next filter that we're going to look at is the sum filter. And in the sum filter, we have a filter that is given by y of n equal to b0 multiplied by x of n plus x of n minus 1. So what this filter is going to take the current input, the previous input, multiplied by a constant, and that will be the output. So let's see what this filter is going to do. So therefore, h of n equal to b0 multiplied by delta of n plus delta of n minus 1. And therefore, h of z equal to b0 multiplied by 1 plus z to negative 1. And from h of z, I can calculate h of e to j omega, which is going to equal to b0 multiplied by 1 plus e to negative j omega. Okay. That's you. Okay. So to plot this as a magnitude and a phase, we can take, since this is complex, e to negative j omega, we're going to do the trick that we've seen before. We're going to take half of that phase, and then we're going to get e to j omega over 2 plus e to negative j omega over 2. And therefore, we can write this as 2 multiplied by b0 e to negative j omega over 2 multiplied by cosine omega over 2. Together? Okay. So therefore, we can plot the frequency response. How does the frequency response look like? If this is omega, if I'm at 0 all the way to a pi, to a negative pi. It's going to look something like this. To be 0. To be 0 multiplied by cosine of omega over 2. When omega is a pi, it's going to be a 0. And therefore, cosine pi over 2 is going to be a 0. So therefore, h of e to j omega is going to look something like this. Now we can also plot the phase since we have it handy. and the phase when it is a pi to a negative pi. When it is a pi, is going to be negative pi over 2. And when it is negative pi, is going to be pi over 2. Together? And actually, I want to be careful on this filter. I'm thinking back. This could be, the phase could be linear or not linear. We did not establish the conditions for linear or not linear. The FIR filter can have a phase that is linear or not linear. We'll look at the conditions to make it linear, but it could also have a nonlinear phase. Okay, so what is this filter?
Low pass.
A low-pass filter, a crude low-pass filter. Is it clear, everybody? How we plotted the phase? This represents the phase. When omega is pi, the phase is pi over 2, negative pi over 2. When omega is negative pi, the phase is pi over 2. And what do we notice about this phase? Linear. Okay. Another filter. Well, actually, let's see how this filter works. So let's take this filter with B0 that is equal to 1. So therefore, y of n just going to equal to x of n plus x of n minus 1. We said this is a low-pass filter. So let's see if indeed it behaves as a low-pass filter. So I'm going to input two signals. One, what is the frequency of this signal? 0. And another very high frequency, which is going to be oscillating between 1 and negative 1. Together? So if this is a low-pass filter, we expect it's going to amplify this, or it's going to allow the signal to go through, and it's going to try to remove this signal. So let's see what the output of this filter is going to look like. Okay, so the output is going to be x of n plus x of n minus 1 is going to start with a 1. Then x of n plus x of 1 minus 1 is going to become a 2. Then it's going to be a 2, a 2, a 2, a 2. Agree? So first one is going to, depending on the initial conditions, let's say the initial condition was 0, so x of negative 1 was 0. Or x of negative 1 is a 0, so therefore it's going to be a 0. Okay. And then we're applying a signal that is oscillating. The first one is going to be a 1. Then we're going to take the current input, which is negative 1, added to a 1, is going to be a 0. Then we're going to take positive 1, added to a negative 1, is going to be a 0, a 0, a 0, a 0. And therefore, we see that indeed it allowed the signal to go through, and it removed the second signal. Okay. Okay, let's look at another example. And this is a difference filter. Y of n equal to a constant multiplied by x of n minus x of n minus 1. What do you think this filter is going to be? A high pass. How do we get h of e to j omega from this filter.
You go to Z first, right?
Yeah. I mean, remember, we just done it twice. Let's keep in mind, if we have a difference equation, we can always get h of n. We can take from h of n, get h of z. From h of z, we can get h of e to j omega. So again, if we have any of this information, we should be able to go from any other to any other representation. This is going to be delta of n minus delta of n minus 1. And therefore, h of z is going to equal b0 multiplied by 1 minus z to negative 1. And therefore, we can get h of e to j omega, which is going to equal to b0 multiplied by 1 minus e to negative j multiplied by omega. Okay, so we're going to do similar trick to what we've done. We're going to take half the phase, e to negative j omega over 2. We can write this as e to j omega over 2 minus e to negative j omega over 2. And therefore, what is this going to equal to? b0 e to negative j omega over 2 multiplied by a sign, and we have to add a j2. So 2 multiplied by j multiplied by sine omega over 2. How do I get rid of this sign? I can write this as b0 e to negative j omega over 2 multiplied by e to j pi over 2 multiplied by 2 multiplied by sine omega over 2. So therefore, this is equal to 2b0 e to negative or e to j pi over 2 minus omega over 2 multiplied by sine omega over 2. Okay, so we can plot the frequency response and the phase. So this is going to be a sine. When it is a pi, it's going to be the maximum, which is equal to 2b0. Something like that. And this is the magnitude h of e to j omega. And the phase of h of e to j omega, this is the magnitude. When the frequency is a pi, it's going to be a 0. When it is negative pi, is going to equal to a pi. And between them, they're going to connect together. Something like that. And when omega is 0, this is pi over 2. Together? Again, this has a linear phase. Okay. Any questions? Okay. So before we move on, since we've been talking about the phase and plotting the phase, let's just spend a few minutes talking about the importance, why is it important to have linear phase? And of course, this applies to any system, to any filter, to any system that takes an input and generates an output, whether it's continuous or discrete, whether it is a filter or any circuit. So let's look at this system. Where we are applying x of n, and we are generating y of n. And this system has a phase that is omega multiplied by t delay. So the phase is omega, negative omega multiplied by t tau delay. And therefore, if I come here and I plot this phase, looks something like this. When I am at any frequency, I have a line that looks like this, and at any frequency, if this is omega 1, the phase is going to equal to negative omega 1 multiplied by tau delay. If I am at negative omega 2, I'm going to have a phase that is omega 2 multiplied by tau delay. Together? Okay, what's special about this? First of all, what is the slope of this curve that we plot of the phase? Negative tau delay. Yeah. The slope is negative tau delay. Omega 1 get multiplied by negative tau delay omega 1. Okay. So let's see now what happens if I applied a signal to this system. And the signal that I'm applying is omega 1 multiplied by n plus cosine omega 2 multiplied by n. Now somebody might tell me, oh, what is the magnitude? You just showed us the phase, isn't it? For the simplicity, I'm just going to assume the magnitude. What is the magnitude? Just a 1. Make sense? Because I'm not focusing on the magnitude, but you can incorporate the magnitude later. So just a system that has a phase that is equal to negative omega multiplied by tau delay. Okay, so you came to this system. We applied this input to it. The output of this system, y of n, is going to equal to cosine omega 1 multiplied by n minus omega 1 multiplied by tau delay plus cosine omega 2 multiplied by n minus omega 2 multiplied by tau delay. Again, if I have a frequency here that is omega 2, this is going to have a phase that is negative omega 2 multiplied by tau delay. Is that clear? Mm-hmm. Everybody remembers that? When you put this through a filter, if this was not a 1, if this was 0.5, then this is going to get multiplied by 0.5, and the phase is going to be added to whatever the phase at that frequency. Okay, so everybody knows where this is coming from? where this is coming from. We take a sinusoidal signal. We see at that frequency what is the phase, and we add it to the phase at the output. Okay. So there's nothing new here. Now I'm going to write this as cosine omega 1 multiplied by n minus t delay plus cosine omega 2 multiplied by n minus t delay. Took the n as a common factor, the omega 2 as omegas as common factor. Now, how can I write this in terms of this signal? What is this signal in terms of x of n?
N minus tau delay.
Excellent. This is equal to x of n minus tau delay. What does all that mean? Means the signal went through the system with no distortion. It just got delayed by tau delay. Does that make sense?
Yeah.
All the frequencies were delayed by the same amount of time. What is we have two, in the input here, we have two frequencies, omega 1 and omega 2. Omega 1 was delayed by tau delay, omega 2 was delayed by tau delay. And as a result, the whole signal was delayed by tau delay. This is only possible when the phase is linear. If the phase is not linear, I would not be able to write this like this. Is that clear, everybody?
Yeah.
So therefore, having linear phase all frequencies are delayed by the same amount of time. And that means there is no distortion. Okay. Now keep in mind, if I were to write this phase is different than this phase, isn't it? So they do not have the same phase. But if I took the frequency as a common factor, then I should have the same tau delay. Make sense? So if I have a signal, if I have two signals, cosine omega 1 n plus cosine omega 2 n, I put them through the system, and at the output I have cosine omega 1 n plus pi over 4 plus cosine omega 2 n plus pi over 4. Is this system going to distort the signal or not?
No.
It will distort the signal because they have the same phase even though they have different frequencies. Does that make sense? Remember, the phase here is different. This phase is different than this phase. Okay. Now the other thing that also we need to know is that this signal, what happened to the signal that we inputted? It got delayed by tau delay. What is that tau delay? Is the slope of this curve. Negative tau delay.
The steeper the slope, the more delay.
Yes, the steeper the slope, the more delay. If the slope was 0, what does that mean? There's no delay. The steeper, the more delay. Okay. Okay. So with that, let's look at the conditions that will ensure. So is the having a linear phase, is that a quality that is desired or not? It is, because we don't want to distort the signal. Now, although we showed this for two frequencies, you can think of these two frequencies as these two frequencies are in the pass band. Make sense? If during the pass band of the filter, the phase is linear, then the signal is going to go through without attenuation. However, if the phase is not linear, then at the output, even though this filter is going to filter the signal, remove these frequencies, is also going to distort the signal that are going through it. How much distortion that is going to cause will depend on how the phase looks like, how far it is from being linear. Does that make sense? Everybody? Yeah. Okay. So with that, we're going to look at what are the requirements on H of n in the FIR filter to have linear phase. And the answer to that is that if H of n is causal and has length that is equal to n, then if H of n is equal to plus or minus H of n minus 1 minus n, it means the filter has linear phase. And therefore, we need to have symmetry about n minus 1 divided by 2. And this symmetry can be either odd or even symmetry. Okay. So again, the condition is that H of n equal to plus minus H of n minus 1 minus n. Okay, so what this answer says, if you have a filter, and this filter has a symmetry such that if you take the middle of the filter, the impulse response of the filter, and there is a symmetry, then that filter will have linear phase. And we'll see the different cases. Okay, so let's look at the first case, which is when we have so we're going to have 4 cases. Where are the 4 cases going to come from? N can be even or odd, and we could have odd or even symmetry. So 4 different combinations. So the first case, or the first type, call it type 1. Is when we have n that is odd and we have even symmetry. Okay, so if you look at the impulse response, it might look something like this. This is the axis. I'm going to plot the impulse response with blue to okay. So at 3, I'm going to have impulse that looks like this. What do you notice about this filter? What is N? 7. Yes. Because we're starting from 0. So N is odd, and I have even symmetry. Around the middle, which is the N minus 1 over 2, which is 7 minus 1 over 2, which is 3. This is symmetrical to. There is a symmetry around n equal to 3. So this means this filter is going to have a linear phase. Okay.
It's because 3 is the middle.
Because, say it again,
So 7 minus 1 divided by 3 is 3.
By 2.
That's where the center of.
yeah, that's where the symmetry has to be,
Okay.
around that point, the n minus 1 over 2. Okay. The second case, and we're going to derive this, why this is the case in the next slide. So, but for the time being, we're going to put all the different cases. The second type 2, is when we have n that is even, and we have even symmetry. So in this case, we might have so 0, 1, 2, 3, 4, and 5. And therefore, n equal to 6. 6 minus 1 is 5 over 2, 2.5. So I have to have a symmetry around this point here. And I have an even symmetry. Make sense? Okay. Now if I look at this filter type, I can write h of e to j omega as equal e to negative j omega multiplied by n minus 1 divided by 2 multiplied by the summation from n equal 1 to n over 2 to h of n over 2 minus n multiplied by cosine omega of n minus 1/2. And we're going to derive this expression for the first case later. So I'm just going to list it as is without deriving it, but we'll derive it for one of them. And the reason we have this is because we can tell what kind of filter we can design by looking at the impulse response and the symmetry. Okay. So if I look at this filter, what is h of e to j omega when omega is equal to a pi? Half. How about a 0? Because we're multiplying it n minus half. So whatever is going to get multiplied by half is going to be the cosine of pi over 2. Together? So in n0, this is going to be cosine pi multiplied by 1/2. When n is 1, pi multiplied by 1/2, and so on. So therefore, h of e to j omega is equal to a 0. So therefore, can we use this filter to design a high-pass filter or band-stop filter? Can we use this configuration and even symmetry to design a high-pass filter? We cannot. Why? Because h of e to j omega is going to equal to a 0. Anybody confused? Again, because at the high frequency, this type of shape is always going to remove this high frequency. Therefore, we cannot use it for a band stop filter or for a high pass filter. Okay. The next configuration is type 3. And in here, we're going to have n odd, and we're going to have odd symmetry. So n is odd, 0, 1, 2, 3, 4, 5, and 6. So we're going to have something that might look something like this. See the symmetry? The odd symmetry around the 3. Okay. So if we calculate h of e to j omega, we can show that h of e to j omega can be expressed as j multiplied by e to negative j omega of n minus 1 divided by 2 multiplied by the summation of 2h of n minus 1 divided by 2 minus n sine of omega multiplied by n. And therefore, if I look at h of e to j pi is going to equal h of e to j 0, which is going to equal to a 0. Because of the sine omega, when omega is 0, when omega is a pi, this all is going to be 0. And therefore, can we use this for low-pass filter? No. High pass filter? No. Band stop filter? No.
So you can't use it. Bin.
Can't be used.
So only band,
Huh? What is it?
only band pass.
Can't, yeah. Can't. Can't type can't. Cannot. Let's emphasize it. Okay, so if you have an odd symmetry and n is odd, then the filter at 0 and at pi is going to have an amplitude of 0, magnitude of 0, and therefore that is not going to be, it's not be possible to use it for a low pass filter or a high pass filter, nor a band stop filter. Okay. The fourth type is when we have n even and odd symmetry. In even and odd symmetry. Okay. Because all of these are h of n. Okay, so in this case, we can write h of e to j omega equal to j multiplied by e negative j omega n of n minus 1 over 2 multiplied by the summation from n equal 1 to n over 2 to h of n over 2 minus n sine omega of n minus 1 half. And if you look here, h of e to j omega h of e to j 0 is going to equal to a 0, and therefore we can't use it for low pass filter. Okay. Any questions? Okay, so apparently, as you can see, the type of the filter and the symmetry that it has will give us linear phase, but also will restrict what type of filter we can build with it. Okay, so let's look at the case when n is odd and we have even symmetry, and derive the expression for h of e to j omega. Sounds good? So n is odd and even symmetry. N are odd and even symmetry. So I'm going to write here C next page. And since this is lots of typing, I just typed it ahead of time. it's going to be, okay, so h of e to j omega, the summation from 0 to n minus 1, h of n, e to negative j omega n. Agree? Now what we're going to do, we're going to split it into 3 parts. I'm going to take the summation till here, then I'm going to take this component, then the rest of the summation. So I'm going to take the summation from 0 to n minus 3 minus 3 over 2, and then I'm going to take, which is going to represent this part, I'm going to take the summation from n plus 1 over 2 to n minus 1, which represent, so let's keep it with the colors, this represented by this, and then we have the middle one, which is this one here. Sounds good? So just I broke down this summation into 3 parts. Instead of 0 to n minus 1, I took it from 0 to n minus 3 over 2. And then I took it for the case when it is n minus 1 over 2. So this represents the n minus 1 over 2. And then from n plus 1 over 2 to n minus 1. Sounds good? Okay, we'll finish this in the next class. You can look at it. I'll post it with the notes, but we'll finish it next class. Any questions?
Just so we're clear, when's the exam duration from?
Well, he's got to go write it.
I'm going to write it so I don't change my mind after. So what did we agree to?
Thursday, 1 p.m.
Exam on will be posted.
That's perfect for me.
Don't leave. On Thursday, this is 3:30 at 1 p.m. and you will have 23.59 to finish. Sounds good? Yeah. I already changed my mind. Here is 24 hours. You're welcome.
Just let me know if you have a moment.
Yeah, sure.